Okay, so let's take a look at this. Wow, this is gonna be heavy. All right, so presumably there's a force acting along this. That's terrible. I'm just gonna erase that. It's so hard to draw. Oh, that's pretty good. Okay, so we'll call that the tension. Okay, so the tension of this cable is acting this way, right? And of course that has a horizontal component and a vertical component. Okay, so this would be T sine 58. This would be T cos 58. Would be that little bit right there, right? So we got two components. And this is just SOHCAHTOA, right? This is the adjacent side, that's the opposite side, right? There's going to be a force downward on the beam here at 5 meters, right? And this is going to be 85 G, where G is 9.81, right? Okay, and that's going to be down, and that's at 5 meters, right? Because it says so, right? And then the beam is 12 meters long, and so the force of gravity is going to be acting down on the beam. I'll draw it there. It doesn't really matter where I draw it. And that's going to be 350 G. So 350 times 9.81, right? Okay, that's not grams, that's times 9.81. Okay, and that's going to be at 6 meters. Because all beams are uniform, right? So if it's a 12-meter long beam, the center of gravity will be at 6 meters. And we say that the force acts at the center of gravity, at the very center of the object. Okay? Okay. And then, yeah, I think we're all set. We got all the forces acting on. Oh, and then, sorry. Then we also have the wall exerted, whatever the wall is exerting in the y direction, and then whatever the wall exerts in the x direction. We'll call that. Okay, so this is our unknown. We want to know that, and that. Okay. So the first thing I'll do, let's set up the wall in the x direction, right? Or let's just set up the x direction. Sorry. So in the x direction, we've got the wall in the x direction. Okay, and then this would be to the left, this T cos 58. So I'm going minus T cos 58. Okay, and then that's 0. Okay. All right, and then let's look at the y direction. Okay, so we've got in the y direction, we've got the wall in the y direction, right? We've got the weight of the box, so minus 85 G. We've got the weight of the beam, so minus 350 G. Then we've also got this part of the tension, the part that's vertical, right? So plus T times sine of 58. It's a vacuuming kind of day here. All right, so this is up, this guy's up, gravity is down, this part of the tension is up, and then that's 0. Okay, and then by the way, this can't be solved. We don't know this. We don't know this, so we can't solve it. Let's set up our torque, though. We will be able to solve our torque. Okay, so let's torque about the left side. So let's say that this is our torquing point. You always have to have a point which we torque about, right? So if I torque about this point, the wall in the y direction is at 0, so 0 times the wall in the y direction. Of course, the wall in the x direction doesn't exert a torque about that point. Okay, and then this, okay, so it's neither clockwise nor anti-clockwise, right? And then the 85 kilograms is going to be at 5 meters, right? And that's going to be a positive torque, so plus 5 times 85 G, where G is 9.81, right? We're talking about I'm just shorthanding it here, right? And then we've got the beam itself, right? Okay, so plus 6 times 350 G, right? And then we've got this cable that's attached here. Now it's 1 meter in from the end, and so this is at 11 meters from the left side, right? Okay, so that would be minus 11 meters, and then the torque, this component is perpendicular to it, so we'd say T sine theta. Or we would just simply, since torques generally, right, are RF sine theta, we just generally use the sign. I mean, it works out either way. I always just think of it as this component of the force is perpendicular, so we use that. And that's 0. Now, because we chose a spot where an unknown force was acting, this component just cancels right out, okay? So now we're all set. We've got an equation with one unknown. It's not nice, but it's not too hard, right? Okay, so we can just do this with a little bit of algebra, right? Okay, so I'm going to go, this time I'm not going to use my solver. I'll just go 5 times 85 times 9.81. Okay, plus 6 times 350 times 9.81. And then I'm going to divide by, we'll get that answer. And then divide by 11. Divide by sine of 58. With any luck, 2,655.3. Yeah, there we go. So my torque is, or my torque, God, sorry, my tension is 2655.322. Okay. Tensions are always positive. Cables always pull. All right. Now what I can do is I can plug into this guy here. Okay. I can now plug into that and get the wall in the y direction. So wall in the y direction minus 85G. Here, let's draw a little line here to make this. Okay, minus 350G plus 2655.322 sine. Okay, so do you see what I'm doing? I got the tension here, right, from this expression, and I'm just going to plug it in for that, and now the only unknown I'll have is Wy, and I'll be able to figure that out. Okay, so let's do this. Wy is going to equal 85 times 9.81 plus 350 times 9.1 minus the answer I just got times sine of 58. And that's 2015.5 newtons up. Okay, so my and since it's positive, it's up. All right, and now we can solve this guy, right? So this is the way it always works. You get the tension and you plug it into this. You plug it into this to get the wall thing, right? Okay, so let's just plug that in. Wall in the x direction minus 2655 cos 58 equals 0. Okay, so I'm just going to grab that number, the 2655 times cos 58, and I get 1407.1. Now the fact that it's positive means that it's to the right. And the reason it's positive is that we said that this arrow going to the left that represented that component was negative, so we threw that minus sign in there like that. Okay? All right. I hope that helps.